Hey folks, I've got an interesting two-dimensional example for you guys to try, and I call it the clock example. And this is actually passed down to me from a previous teacher. Uh, so here's the deal. You've got a regular clock like in the classroom that has a minute hand, and we're going to focus on the minute hand, okay? And I've kind of drawn a little sketch of the clock with my beautiful artistic abilities are. And let's say the minute hand at this moment is at the noon position. Okay, so the 12 o'clock position. And I'm going to give you some data. Okay, let's say the radius of the minute hand, so from the pivot to the outer edge, let's say it's 10 centimeters. Okay, and we are going to focus our attention on just the tip of the minute hand. Okay. So here's what I would like to calculate about the minute hand, the tip of the minute hand. I want to calculate its average velocity as it travels from the noon to the 3 o'clock position. Okay. And also like to calculate its average acceleration, linear acceleration, as it travels from the noon to the 3 o'clock position. Okay. Now to make this really clear, how long does it take a minute hand to go from the noon position to the 3 o'clock position? Well, that's 15 minutes. So that's the first big hint for you. Again, I'm looking for averages. Okay. Now, some other things that I'd like to try so we all agree on our answers. We're going to have exact answers, and we're going to measure everything in centimeters and minutes. Okay, so like a velocity would be centimeters per minute, and an acceleration would be centimeters per minute squared. That's going to keep our numbers semi-reasonable. And again, I want exact answers, so you don't need a calculator for this one. Finally, some information that you might need as review. You may or may not need these as review from last year. Okay, for something traveling in a circle, its tangential velocity is 2 pi r over t, t being the period of one complete revolution. So this is how fast the thing's moving. Like if you're in a car going in a circle, your speedometer would read that number, whatever 2 pi r over t is, circumference over time, distance over time. And then you also might or might not need the equation for radial acceleration. That's the inward acceleration of anything traveling in a circle. And that is v squared over r. And that's actually coming up. We're going to talk a lot more about that very shortly here. But for now, you may or may not need one or both of those equations. Okay. So again, what I want is the average velocity from the noon to the 3 o'clock position and the average acceleration from the noon to the 3 o'clock position. Now, normally, if I were in class right now, I would pause and I would give the students a couple minutes to try this out. And normally what I do is I say, hey, get the velocity, and if you get that, check it with me, and then go back and work on the average acceleration. Okay. So I would strongly urge you to try that really quick. But I'll pause for a sec and then I'll go through my solutions. All right, so for average velocity, what we need is displacement over time, okay? So displacement is going to be delta r over time because it's a two-dimensional displacement. So I'm going to write the displacement vector in unit vector notation. I'm going to use the center of the clock as my origin, so that's 0, 0. So the starting position, the position at noon, in centimeters, well, we're at 0 I hat because we're right up here, and then we're plus 10 j hat centimeters. And then when the minute hand is at the 3 o'clock position, the position vector is 10 I hat plus 0 j hat centimeters, okay? And again, how much time has elapsed? Well, that is 15 minutes to get from the noon to the 3 o'clock position. So if I do delta r, okay, so I'm going to take this minus that, the position vector at 3 o'clock minus the position vector at noon. I'm doing final minus initial. You get 10 minus 0, so you get 10i, and then you get 0 minus 10, so minus 10j centimeters. And then the average velocity is simply that divided by 15 minutes. So 10 divided by 15 is 2/3. So we got 2/3 I hat minus 2/3 j hat centimeters per minute. Okay, so that is the average velocity of the minute hand, the tip of the minute hand, as it travels from the noon to the 3 o'clock position. Notice it's to the right and down, which makes sense. On average, the minute hand is moving to the right and down. Okay. Now, notice that what a lot of people will try to do in a problem like this is they'll try to use this equation. V average is, they would do the V at the noon position plus the V at the 3 position divided by 2, the average velocity equation. However, we can't use that here because the acceleration of the minute hand is not constant, okay? And I'll get to that in a minute, okay? No pun intended. Now, I'll give you guys a sec. Now that you have the average velocity, the next thing you're trying to find is the average acceleration from the noon to the 3 o'clock position. And remember, what's the definition of average acceleration? That always works. Okay, so if you want a second to give that a shot, now would be a good time to pause the video and give that a try. All right, so what's the average acceleration? Well, average acceleration, okay, is defined as change in velocity over time. So I need the change in velocity. I need the velocity at the noon position and the velocity at the 3 o'clock position of the tip of the minute hand. Now, I'm going to start the noon position. When the minute hand is at the noon position, its velocity is to the right. So this is the V at the noon position. What is that? Well, here I have to use my V equals 2 pi r over t equation. So off to the side here, the magnitude of the velocity at any moment is 2 pi r over t, which is 2 pi. The radius is 10 centimeters. How long does it take the minute hand to do a complete lap? Well, that's 60 minutes, okay? So your velocity is 20 pi over 60, or pi over 3 centimeters per minute. Okay, so that's the magnitude of velocity. By the way, that's about 1 centimeter per minute, which if you think of a regular clock in a classroom, the tip of the minute hand moves about a centimeter a minute if you were watching. All right, now I got to write the velocity at each of these two positions in unit vector notation. So at the noon position, we're moving to the right, okay? So that would be pi over 3 I hat plus 0 j hat centimeters per minute. Now, how about the 3 o'clock position? So when the minute hand's at the 3 o'clock position, well, now it's moving downward. So we're going to have a 0 I hat and then a minus pi over 3 j hat centimeters per second. To find the average acceleration, I got to do the change in velocity. So final minus initial. So I'm doing V at 3 o'clock minus V at noon. So delta V, okay, is 0 minus pi over 3. So negative pi over 3 I hat. And then negative pi over 3 minus 0, which is also negative pi over 3 j hat centimeters per minute. Oop, and above here, this should be a minute, by the way. Sorry about that. All right. Now, our acceleration average is simply the change in velocity I just got divided by time, which is 15 minutes. So I'm taking each of these divided by 15. So like pi over 3 divided by 15 is pi over 45. So my answer is negative pi over 45 I hat minus pi over 45 j hat centimeters per minute, okay? So that is the average acceleration of the minute hand, the tip of the minute hand as it goes around the circle. Now, by the way, a quick note on that, both components are negative. So on average, like when the minute hand's here, the acceleration is inward, which is down and to the left on average, okay? Now notice something else. We did not use our radial acceleration equation. Didn't need it, and it wouldn't be useful here anyway. That gives you the magnitude of the acceleration at any moment, but the acceleration is not constant. The magnitude of the acceleration is constant. It's whatever v squared over r is, pi over 3 squared divided by 10, okay? However, the direction of the acceleration is changing. That direction is always toward the center. So as the minute hand goes in a circle, the direction of that acceleration changes, meaning it's not a constant acceleration. Remember, vectors are magnitude and direction. If either is changing, the magnitude or the direction, then it's not constant. So we don't have a constant acceleration, so we couldn't use our constant acceleration equations. We had to use the equations that always work, which is average velocity is change in position over time, and average acceleration is change in velocity over time. A quick reminder, the other two equations that always work is v at any moment is dr dt, and a at any moment is dv dt. Those are the only four equations that always work. So I hope that example was interesting, and thank you very much.